Jai Hind students, how are you all? I'm very sure you all must be very fine and working real hard towards achieving your dreams, isn't it students? Well, before we start this session, I must share a thought with you as usual. The struggle you are in today, students, the struggle you are in today is the developing the strength you need for tomorrow. Again I repeat students, the struggle you are in today is developing the strength you need for tomorrow. So students, what I mean is, don't hesitate to put in that extra bit of effort at present situation, because in near future you are definitely and surely going to get rewarded. So put that extra effort. So there shouldn't be any lag in your effort and sincerity, right? So with that students, let's begin this session. And since we have covered the theoretical concepts of classification of magnetic materials, now in this session, let's recap the entire thing, isn't it? And also, let's recollect the formulas we have studied in electrostatics, electricity, right? So there's a correlation, there is a great relationship, there is a close relationship between electricity and magnetism. In this session, we will discuss various formulas which we have discussed in electrostatics and now in magnetism, and try to find that relationship so that it becomes much easier for you to remember all those formulas. So this chart which we are going to discuss today would be very important for you before any exams, right? It will give you a quick summary of everything which we have discussed in those two units. So let's start students. So I've prepared this column. One is with regard to the electrostatics, electricity, and the other one is related to magnetism, right? Let's see how they are closely related. And the physical quantities which are analogous to each other, right? So, in electrostatics, we discuss charges which are at rest. There are two types of charges, positive charge and negative charge, isn't it? Two types of charges are positive charge, that is represented by plus Q, and negative charge, that is represented by minus Q. In magnetism, whatever role charge plays, the same role is played by poles. And we are aware, poles always exist in equal and opposite pairs. So here, in place of charge, we'll make use of magnetic poles in magnetism. So there are two poles, one is the north pole and the other one is the south pole. So north pole. In a magnet, these two poles are of equal strength but opposite nature. So north pole, its strength is represented by plus M. So students, the point to be noted over here is, north pole is analogous to the positive charge, while south pole, whose pole strength is minus M, is analogous to the negative charge. Clear students? So here the concept of charge is used, and here the concept of magnetic poles are used, right? Okay. Second, very important one. The constant K over here is 1 over 4 pi epsilon naught. Epsilon naught is the absolute permittivity of vacuum or free space. Isn't it students? In magnetism, this K constant is mu naught divided by 4 pi. Here, mu naught is obviously absolute permeability. Here it is permittivity, and here mu naught is the absolute permeability of free space or vacuum. Clear? Third, this is in case of vacuum. In case of medium, K is 1 over 4 pi epsilon. Epsilon is absolute permittivity of the medium under consideration, isn't it? Here students, in magnetism, in case the poles of two magnets are placed in a medium, then K, the constant, would be given by mu by 4 pi. So mu would be the absolute permeability of the medium under consideration, of the medium in which the two poles are placed, right? Fourth, we are aware of relative permittivity, isn't it? It is defined as the ratio of the absolute permittivity of the medium to the absolute permittivity of free space. Thus we are aware of this relative permittivity is also known as dielectric constant of the medium, isn't it? In the similar manner here, the relative permeability, this is the relative permittivity, this is the relative permeability, and it is defined as the ratio of absolute permeability of the medium to the absolute permeability of free space. It's very simple, students. If you are aware of all the formulas in electrostatics, then you won't find any difficulty in remembering the corresponding formulas in magnetism. It's so very simple, right? Then, fifth point. Students, we are also aware about the relationship between permittivity and susceptibility, isn't it? So, in electrostatics, the relationship was epsilon r, it is the relative permittivity, it is equal to 1 plus electric susceptibility. Chi E is the electric susceptibility. Chi E, it is the electric susceptibility. While in magnetism, relative permeability is equal to 1 plus chi m. Here, chi m is the magnetic susceptibility. It is the magnetic susceptibility. Clear, students? Right? Okay. Sixth point. Very, very basic one. Here, in case of charge, we discuss electric field. Electric field is due to a charge. Magnetic field is due to a current element or due to a pole, isn't it? So, electric field, students, as you are aware, it's defined as limit Q naught tends to 0, the electric force divided by Q naught. So electric field at a point due to a source charge is defined as the electric force experienced per unit test charge placed at that point, isn't it? Here, the magnetic field is defined as limit M naught tends to 0. This is a test pole. It approaches to 0, means its pole strength is considered to be infinitesimally small or negligible. So it will be equal to Fm, this is the magnetic force, divided by M naught. So the magnetic field at a point due to a source pole is defined as the magnetic force experienced per unit test pole placed at that point. Clear? So students, seventh. So the electric force is given by QE, isn't it? Electric force is given by QE. In case it is positive, then it will experience force along the direction of the electric field, and in case it is negative, then it will minus Q, indicating that in that case it will experience electric force in a direction opposite to that of the electric field, right? Similarly, over here, the magnetic force. Look, the magnetic force, it would be equal to M naught into B, or simply M into B. In place of charge, it will be pole strength, in place of electric field, it will be magnetic field. For north pole, it's plus M, isn't it? For north pole, it's plus M. So in that case, North Pole experiences magnetic force along the direction of the external magnetic field. While for South Pole, it will be minus M. So South Pole will experience magnetic force in a direction opposite to that of the external magnetic field. Clear? Okay. Next is the electric force between the 2-point static charges, which is the Coulomb's law in electrostatics. That is, students, in magnitude it is K, which is 1 over 4 pi epsilon Q1 Q2 divided by R square. Right? This is K. In magnetism, the magnetic force between the 2 poles, right, of different magnets, obviously placed in air or vacuum, it will be given by K. Here K in magnetism is mu naught by 4 pi. K in place of Q1 Q2, it will be product of the magnitude of the pole strength. It will be M1 M2. It will be M1 M2 divided by R square. R is the separation between the 2 charges over here and between the 2 poles in case of magnetism. Right? Okay, students. Ninth, electric field. If you substitute this value of Fe over here, 1Q get cancelled. So electric field due to a source charge is given by K, that is 1 over 4 pi epsilon source charge divided by R square. This is the source charge, isn't it? Similarly, magnetic field in place of 1 over 4 pi epsilon, in magnetism the constant is mu naught over 4 pi. This is what we have discussed over here. Here K is 1 over 4 pi epsilon, and correspondingly in magnetism the value of K is mu naught over 4 pi. So in place of source charge, here it will be source pole having pole strength M divided by R square. So very simple, isn't it? Okay. 10th. Here we have discussed electric dipole, which is the arrangement which comprises of 2 equal and opposite charges separated by a finite separation, isn't it? And magnetic, or rather electric dipole moment. First and foremost, we will discuss the electric dipole moment. It is given by product of magnitude of the charge and the distance between them. And the distance, that is the dipole length, that is the distance between the negative charge and the positive charge constituting the dipole, is considered to be a vector quantity having direction. Direction is from negative charge to positive charge. So its direction will be also from negative charge to positive charge. Clear? This is the electric dipole moment. So here, students, it will be the magnetic dipole moment. This is the electric dipole moment, it is the magnetic dipole moment. Magnetic dipole is a fundamental arrangement comprising of equal and opposite poles, isn't it? Separated by a finite separation, obviously. In place of charge, it will be defined as the product of magnitude of either of the pole strength and the magnetic length. Magnetic length in the article we have considered to be 2L. So here it is the dipole length directed from negative to positive. Negative is analogous to south, positive charge is analogous to north pole. So here the magnetic length is directed from south to north, and accordingly the magnetic moment is directed from south to north. Clear, students? Negative charge is analogous to south pole, positive charge is analogous to north pole. So here the electric dipole length or the dipole moment is directed from negative charge to positive charge. Similarly, students, in the case of magnetism, the magnetic length or the magnetic dipole moment is directed from south pole to north pole. Right? Okay. 11th. Now, students, if you remember, we have done three articles. The expression for the electric field at a point on the axial line. So there, the expression for the electric field is E axial. It is 1 over 4 pi epsilon twice PR. P is the electric dipole moment and here in denominator it is r square minus a square whole square. R is the distance of the observation point on the axial line from the center of the dipole. Clear? Here students, B axial, the magnetic field at a point on the axial line of a magnetic dipole. In place of 1 over 4 pi epsilon, we will use mu naught over 4 pi 2. Same. In place of electric dipole moment, here it will be magnetic dipole moment. R, here R is also the distance of the observation point on the axial line from the center of the magnetic dipole, right? R square minus A square. Here it will be R square minus L square. Here the distance between the south and the north pole is considered to be 2L. So from the center of the dipole, the distance of either of the pole would be L. And in this case, you consider the distance of either of the charge from the center of the dipole to be A, right? So no difference at all. And if you remember students, in case of axial, the direction is along the direction of the dipole moment, that is from negative charge to positive charge. Its direction is from negative to positive. So here, the direction of the B axial would be from same as the direction of the magnetic moment or the magnetic length, which is from south to north. Clear students? Okay. 12th. Now for a short dipole. For a short dipole, that is when R is very, very large as compared to A. In that case, A square can be neglected. So what we get is E axial, it is equal to twice P divided by 4 pi epsilon, will be left with R cube. Clear students? Direction obviously will remain same from south to north. Here, for a short dipole, that is when R is very, very large as compared to L, then B axial, it is equal to mu naught over 4 pi, this will remain same, twice M divided by R cube. You can remember the formula from the corresponding formula in electrostatics. Clear students? So these are the 12 set of formulas. There are still some other comparison as well, right? Okay students, 13th one, E equatorial. This we are aware, it's given by 1 over 4 pi epsilon P divided by R square plus A square to the power 3 by 2. And students, you must remember, at any point on the equatorial line, the electric field is directed in a direction opposite to that of the electric dipole moment. That is, E equatorial is directed from positive charge to negative charge. So its direction is from positive charge to negative charge. Right? So, now the corresponding formula in magnetism for B equatorial. In place of 1 over 4 pi epsilon, it will be mu naught by 4 pi, no doubt regarding this. In place of electric dipole moment, it will be magnetic dipole moment. And over here, R square plus L square to the power 3 by 2. Right? Direction is from positive charge to negative charge. In magnetism, it will be from north pole to south pole. That is, B equatorial is directed in a direction opposite to that of the magnetic dipole moment. So its direction will be from north to south. Okay. 14th. For a short dipole, that is when R is very, very large as compared to A. So in that case, E equi. Here A square can be neglected in comparison to R square. So we will be left with P divided by 4 pi epsilon R cube. Direction will remain same, that is positive charge to negative charge. Here students, for a short magnetic dipole, that is when R is very, very large as compared to L. So here L square can be neglected in comparison to R square. So we will be left with mu naught M divided by 4 pi R cube. So the direction obviously will remain same from north to south, right? 15th. Now this is very important. For a short electric dipole, E axial divided by E equatorial, it is 2:1. We have discussed the formula for E axial for a short dipole in the 12th point, isn't it? It was twice P over 4 pi epsilon r cube, and E equatorial is P over 4 pi epsilon r cube. So for a short dipole, if you divide these two, we get E axial by E equatorial as 2:1. The same result is valid in case of magnetism as well. So for a short magnetic dipole, what we get is B axial divided by B equatorial. It is also 2:1. It can be easily verified, right? Okay. 16. Students, for any arbitrary point, due to a short dipole at any arbitrary point, the electric field is given by P over 4 pi epsilon r cube square root of 3 cos square theta plus 1. Theta is the angle which the line joining the center of the dipole to the observation point makes with the dipole length or dipole moment, isn't it? So, for any arbitrary point, this point neither lies on the equatorial line of the dipole nor it lies on the axial line. It lies at any point, right? In case it is equatorial line, then theta would be 90 degree. Cos 90 becomes 0, so we will be left with P over 4 pi epsilon r cube. In case it is on the axial line, so theta would be 0 degree, cos 0 is 1, 3 plus 1 will become 4, so root 4 will become 2, so that will give us twice P over 4 pi epsilon r cube. So that's the formula for the E axial for a short dipole. So this is the expression for the electric field at any arbitrary point due to a short dipole, right? Similarly, students, at any arbitrary point due to a magnetic dipole, due to a bar magnet. The magnetic field, the expression for the magnetic field is same. Remember this formula and you will be easily able to formulate this formula. In place of P, it will be M, magnetic moment. In place of 1 over 4 pi epsilon, it will be mu naught over 4 pi r cube, and rest will remain same. 3 cos square theta plus 1. Theta, again, I must mention, theta is the angle, students, which the line joining the center of the dipole to the observation point makes with the dipole length or the magnetic moment, right? So this is it. 17th. Students, regarding the direction, in this case it is given as tan alpha is equal to half tan theta. Theta, as I have told you, again I must mention, it's the angle which the line joining the center of the dipole to the observation point makes with the dipole length or the dipole moment, right? And alpha is the angle which the resultant field makes with the axial component of the field, right? So this is the case. So same formula holds valid here as well. This will give you the direction of the magnetic field, and this alpha gives the direction of the net electric field at that arbitrary point. So it is again half tan theta. Okay, 18th. Students, we are aware of the expression for the torque experienced by a dipole under the influence of electric field, isn't it? So that is given by torque is equal to P E sin theta, and in vector form it is given by P vector cross E vector, isn't it? So here the corresponding formula is torque is equal to, in place of electric dipole moment it will be magnetic dipole moment, in place of electric field it will be magnetic field sin theta. Here theta is the angle between the magnetic moment and the magnetic field. Here theta is the angle between the electric dipole moment and the electric field. So in vector notation it will be given by M vector cross B vector. So very simple, right? 19th. Students, when we do some work in rotating the dipole against the torque, then that amount of work then gets stored in the dipole in the form of its potential energy. And in the case of electric dipole, the potential energy stored is given by PE cos theta 1 minus cos theta 2. Theta 1 is the initial angle which the dipole moment makes with the electric field, and theta 2 is the final angle. Similarly, in magnetism, the potential energy is given by MB cos theta 1 minus cos theta 2. Clear, students? And in this special case, we have discussed if theta 1 is equal to 90 degree and theta 2 is equal to theta. So cos 90 will become 0 and here it will be minus cos theta. Then U would be given by minus P vector dot E vector. Isn't it? This is a scalar product. Similarly, in this case also, if theta 1 is 90 degree and theta 2 is equal to theta, then potential energy would be given by negative of the dot product of M vector and B vector. This also we have discussed, isn't it? Then students, we have discussed the expression for the minimum potential energy and maximum potential energy. So, U minimum, it is equal to minus PE. It is the condition for stable equilibrium, isn't it? And the dipole must be oriented along the direction of the electric field. And U max, it is plus PE. It is the condition for unstable equilibrium. In this case, the electric dipole must be oriented in a direction opposite to that of the applied field. That is when it is said to be in unstable equilibrium, where its potential energy is maximum. Same in magnetism also. Here, the minimum potential energy is minus MB. This stage corresponds to stable equilibrium. As I have told you, here also in stable equilibrium, the magnetic dipole or the bar magnet must be aligned parallel to the direction of the magnetic field. While U max, it will be plus MB. In this case, potential energy is maximum, therefore it will correspond to the state of unstable equilibrium. And here, the orientation of the magnetic dipole must be anti-parallel or opposite to that of the external magnetic field. Right? Okay, students. 21st. Electric flux. We discussed it. It is a property associated with a surface held in a region of the field. So, total number of field lines crossing through the surface held normally, that is known as the flux, right? So, in case of electric flux, it will be total number of electric field lines passing through the surface normally. And in case of magnetic flux, it will be defined as the total number of magnetic field lines crossing normally through a surface held in a magnetic field. So, mathematically, students, electric flux is defined as scalar product of electric field and area vector. This is electric field is area vector and this is the scalar product. Here, the magnetic flux would be defined as a scalar product of magnetic field and area vector. Right? In calculus, it may be written like this: E vector dot ds vector. And magnetic flux for a plane surface, it will be given by B vector dot ds vector. Is it clear, students? Right? Okay. 22nd. Now look, students. students, we have discussed Gauss's law in electrostatics as well as we have discussed Gauss's law in magnetism, right? Gauss's law in electrostatics states that the electric flux associated with a closed surface, which is the closed surface integral of the electric field, it is numerically equal to 1 by epsilon times the net charge enclosed by the surface, right? This is Gauss's law in magnetism. Gauss's law in electrostatics basically. Now the corresponding law in magnetism is known as Gauss's law in magnetism, which states that the net magnetic flux associated with the closed surface, which is given by closed surface integral of the magnetic field, it is always equal to 0. Why it is 0? Because in place of net charge here it will be net pole strength. And net pole strength enclosed by any closed surface is always 0. It is because magnetic poles always exist in equal and opposite pairs, isn't it? So net pole strength enclosed by any closed surface is always 0. And we have discussed its significance as well. This obviously signifies that magnetic pole always exists in equal and opposite pairs, and also the number of field lines entering a closed surface must be exactly equal to the number of magnetic field lines leaving that surface. Okay, now students, also we have discussed for a point charge, electric field obey inverse square law, isn't it? Here, for an imaginary isolated pole, source pole, the magnetic field obey inverse square law. No doubt regarding this, isn't it? But for a dipole, whether the observation point lies on the axial line or on the equatorial line, the electric field varies with distance r as 1 by r cube. For a magnetic dipole here in magnetism, the magnetic field varies with distance r as 1 by r cube. So look, they are very closely related, right? So I hope you have understood all the formulas, students. So do revise these formulas thoroughly and you won't face any problem in these topics. So that's it for this particular session. Do try to study real well and dedicate yourself completely towards your studies, right? So then do join me in my next lecture. Thank you and stay blessed.